In this video, we'll talk about the cross-sectional properties of beams and how shape in the cross-sectional direction is what allows us to combat the moments that we've built up looking at the longitudinal direction. We've calculated moments using shear moment diagrams, and in this lecture, we'll start to turn the corner and start to look at how beams actually resist those moments. And along the way, we'll find out what structural engineers have in common with bowlers. So be on the lookout for that. When we started talking about beams, we looked at a handful of situations where intuitively we have some thoughts about which beam might be better suited to the task. And in crossing number 1 and crossing number 2, we were looking at the relative lengths of the beams, and we started to get in a little bit to the cross section, but it's really this scenario over here, crossing number 4, where we're looking at a very flat beam versus a very deep beam that we want to get to the bottom of in this video. Why is it that a flat beam is so much weaker or so much poorer at spanning than a deep beam? This is something that intuitively we sort of understand, and in this video we'll try to get at some of the math behind why that is. This was a problem that vexed thinkers such as Galileo and Leonardo. Here you see Da Vinci on the top struggling with the relationship between span and depth. He knew that a deep beam was stronger. He didn't quite get the math right. He didn't really understand the mechanisms at work. He took an educated guess, but was off by kind of one factor of depth. At the bottom you see Galileo trying to do thought experiments. Again, over here in the upper left, you can see him sketching through a problem where he understands intuitively that a deep beam is going to be stronger than a shallow beam. Galileo also did not quite get to the math involved. So what's the problem that we're trying to solve? Well, if we go back to our shear moment diagrams, remember we were looking at loading conditions, looking at reactions, doing our thought experiment where we were sort of going left to right, tracking through what the internal stresses in a beam would need to be to resist the forces to one side or the other. And when we got down to moment, we found ways to calculate the maximum bending moment in a beam given what we knew about the shear. And remember that the maximum moment here is going to be equal to the area of the shear diagram up to that point. So now we want to figure out how a beam actually resists those moments. Once we've figured out the maximum shear, the maximum bending, what properties in a beam do we have to work with that allow us to resist those moments? One way that we talked about was tuning the beam shape to the moment diagram. In other words, providing greater depth where the moment was greatest. And this intuitively we understand, right? A deep beam for some reason seems to be good at resisting moments. This gets tricky, especially if we're working with steel, where we're talking about rolled sections. We have to custom fabricate shapes that change longitudinally. In concrete, as you see down here in the bottom, maybe a little bit easier to fine-tune the shape, but we'd like to also find ways that we can make a consistent section that was tuned to resisting these forces as well. So the key to thinking about this is to sort of turn ourselves 90 degrees, and instead of thinking about the longitudinal shape, to start looking at whether there are ways that we can fine-tune that cross-section to deploy the material in a beam where it's going to do the most good. To get at this, we're going to do a little bit of math here and there. None of it is going to be math that you'll be required to do for the problem sets or for the exams, but it's important, I think, to understanding where the numbers come from and where these figures that we'll use in designing beams actually spring from. To start, though, I want to do a little thought experiment again. I want to go back to this early example where we were trying to think about how moment was building up inside a beam, what bending stress actually was. And you might remember that we said that, okay, well, if we do our free body exercise and we slice a beam and try to sum up all of the forces acting on this free body and think about what we need to resist it, in a simply supported beam, we have an external force. This is before we get to any applied load. And as we track our way along the beam, we have an external force. In this case, it was the reaction that's trying to twist the beam in a clockwise direction. And we talked about needing an internal moment, a set of internal forces that could provide a resisting moment, something that would twist back. Now, typically, we're talking about a very long lever arm, a long-handled wrench for the external force or the reaction. We're usually talking about a much smaller moment arm, much smaller wrench for the internal moment. When we dive in and look really closely at that beam, we can think about that moment really as a couple of forces, as two forces that are linked, but that together provide a single sort of resisting moment or twisting back. In most simply supported beams, and all simply supported beams, that internal moment will consist of a compressive stress on the top of the beam, trying to push the beam together, and a tensile stress on the bottom beam, trying to pull the beam apart. And then notice that the third component, and this is really critical, is that there is a moment arm between them, that these two forces are acting in concert. And you'll notice that the further apart they get, the deeper the beam is, the greater the internal moment they'll be able to develop. In other words, the greater the leverage they'll have, the longer their wrench arm will be to resist the moment that's being applied, in this case, by the reaction. If we want to be sort of more technically accurate about it, it's more than just those two forces. What's actually going on is that every single bit of the beam is going into either compression or tension, depending on where it is. If it's in the top half of the beam, it'll go into compression. If it's in the bottom half, it'll go into tension. And the resistive capacity of that beam, and the reason that we can do this with such a short moment arm, the resistive capacity will build up through an infinite number of infinitely small, we'll call them fibers, even though steel doesn't have fibers, concrete doesn't have fibers. We can think of these as little tiny, infinitely small bits of the material. Every one of those will have a little bit of resisting capacity in tension or compression. And when we build them all up, we basically get a diagram that shows how the top and bottom fibers of the beam are undergoing the greatest stress, tension and compression. The fibers in between have this spectrum. The ones further out are being stressed more highly. The ones closer into the middle are being stressed less. And the total capacity of the beam to resist an external bending moment is basically going to be the sum of those areas. So take every little tiny, infinitely small piece of the beam, figure out its capacity to carry tensile or compressive stress, and then multiply that by an infinite number of fibers in the beam, do some calculus, and you'll arrive at the beam's capacity to do this. Okay, we would like to not do this with calculus. We will come around to a way to do this. The key thing here to look at, though, is that the farther away we get from the center of the beam, what we'll call the neutral axis, the farther away we get, the greater the stress. And remember that the total capacity of the beam is basically those areas. So already we have a way to talk about the relationship of depth to strength. If we have a flat, shallow beam, and we're putting a load causing bending on it, we have these two triangles where basically we have to make that area equal the moment that the beam is undergoing, the maximum moment that the beam is undergoing. In a flat beam, note that those triangles are very, very shallow and very, very long. So the highest stress in both cases is going to be very, very large. If we have a deep beam with the same moment, these two triangles have to have the same area as their counterparts in this beam. But notice that because it's so deep, we have a height here of the triangles that's much, much greater. And therefore, the base of the triangles, which represents the quantity of stress in that edge fiber of the beam, is going to be much less. So to carry the same moment, a shallow beam has to have much higher stresses in its extreme edges. A deeper beam can have much lower stresses. And these triangles are the key to answering the question why a deep beam is more efficient, more effective at carrying a bending load than a shallow beam. Short moment arms require higher forces to resist bending. A longer moment arm requires shorter forces to resist bending, because we have that higher moment arm. Remember, a moment is always equal to a force times a distance. In a deep beam, the resisting moment can be higher because we have a greater distance, and therefore we need less stress, less force. Now, this gives rise to the principle of the neutral axis, where if we want to be really, really efficient about designing our beams, we can actually scoop out material that's being lazy. If we go back for just a second, think about the material that's right around the middle in both of these beam sections. That's not doing much. Those fibers are subject to not very much stress at all. We can take those fibers out, redistribute that stress through other fibers in the beam section, and gain a much more efficient section. If you look at, for example, bones in bird wings, where nature is trying to make them as light as possible, you can see this in action. Bird wings have these kind of Warren truss-like diagonals. They have most of their material on the top and bottom, where they'll go into compression and tension, and the wings have eliminated most of the dead weight that is closest to what would be the neutral axis. These, by the way, come from a book called On Growth and Form by a Scottish evolutionary biologist named Darcy Thompson from about 1900, 1901. A great library of structural examples in nature. The bird wing is one of the most famous ones. Material that's not doing very much work disappears, right? It goes away, and that work is being taken up more by the parts of the beam, the bird wing beam, that's going to be able to do it most effectively. Since the early 19th century, we've done this with beams as well, particularly iron beams, where we're able to roll shapes that allow us to concentrate material in one area or another. And very, very early on, a couple of British builders named Fairbairn and Hodgkinson realized that if you concentrated the material in a beam at the top and bottom, if you added what we call flanges to a simple plate, you could basically concentrate the material of the beam where it was going to be most highly stressed, and therefore get the most kind of leverage out of that area of iron, in this case, to resist a bending moment. These are a whole bunch of experiments that Fairbairn and Hodgkinson did, trying to understand the relationship between material in a cross-section and bending strength. The one that works best, as we know today, is an I-beam, or what we typically call a W shape. We will talk about this figure S, section modulus, here in a couple minutes, but for the moment, let's note that if we move the material in a beam away from the neutral axis, not only make the beam deeper, but also concentrate our material at the top and bottom edges of that beam, S, section modulus, which is basically a measurement of the carrying capacity of a beam in bending, goes up exponentially. So, for example, if we take a 3-inch diameter solid bar, we have a section modulus of 1 cubic inch. We'll get to why cubic inch. This has 7 square inches of area. If we take that area and deploy it a little bit more cleverly, you can see that we can increase the section modulus exponentially. So we go from 1 to 18.5 inches by making what we call a C-section, or a channel, having flanges on the top and bottom that concentrate more of the material farther away from the neutral axis. That material is going to have more leverage. It's going to be able to do not just more work, but exponentially more work to resist the bending moment on a beam. And finally, here you see a wide flange, same cross-sectional area as a 3-inch solid bar, but you see that it is 50 times better in bending than a solid bar. And this is the logic behind the I-beam. Okay, how do we get there? This is going to be the mathy part. We will talk about 3 interrelated ways of measuring shapes. And this is all about determining not just how deep a beam is, but where the cross-sectional area in that beam goes. So not just how much area we have, but how far away from the neutral axis it is, and therefore how much resistance it can provide for bending. we'll look at 3 of these. I'll go through the math quickly, and then we'll get to this figure section modulus and talk about how we use it to actually design or select beams. The 3 of them are centroid, which is basically finding the middle of a shape, the neutral axis of a shape. This transitional one, moment of inertia, that is an initial measurement of how far our area is on average from that centroid. And then finally, section modulus, a more useful figure that we can actually use to reliably calculate a shape in bending. So to begin with, centroid is basically our neutral axis. In any given shape, the center of mass of that cross-section is going to be the location where, in bending, the material is experiencing no stress at all. You can think of it as the place in the section that is the least efficient place to put material. Basically, what we'll think of it as is a line that equally divides a section's area. There'll be an equal amount of area in the cross-section above, equal amount below, and that will therefore be the location of the neutral axis. If it's a symmetrical shape, then that's easy. So for an I-beam, the neutral axis will just about always be right in the middle of the shape symmetrically. But we can figure this out for irregular shapes too, and this is useful to understanding basically how the principle works. We can break that shape into regular components, find each of those components' areas, and then average the centroid distance for each of those areas by weighting the area of each shape. So essentially what we're trying to do is find the average centroid for a bunch of shapes, and what we'll see is that we can actually pull the centroid up or down depending on how much area we put into a flange. We can look these up. The centroid, for example, for a rectangle is very simple. It's the depth divided by 2. Same for a circle. Where it gets interesting is where we have shapes like triangles. And here you can see that the centroid is 2/3 of the way up. So a line right about here, we have an equal amount of area above and below that line, right? Not in the actual symmetrical center of the triangle, but pulled down somewhat because we have so much cross-sectional area here at the bottom. So don't worry, this is mostly just for kind of fun, but also to see just how important it is to think about flanges and putting areas into beam flanges. So the way that we figure this out, if we have a T-shaped beam, we can find the centroid for these 2 rectangles very easily, right? They're relatively trivial. We can also find the areas. So here we have a 5 square inch web, basically. So the centroid will be 2.5 inches down, the area will be 5 square inches. Here we have a 3 by 6 inch flange on the bottom. And the centroid for that shape will be at 1.5 inches, and the total area will be 18 inches. So what we do is we take a random, what we call a reference axis, we figure out the distance between each centroid and that reference axis, and then we multiply those distances by the total area of each centroid. So here, the web, we have 5 inches, that's the area, times 5.5 inches, that's the distance from the centroid to the reference axis, and we get this figure 27.5 cubic inches. Weird number, but we'll divide some stuff out here in a second. For the flange, you can see we have 18 square inches. The centroid is 1.5 inches from the reference axis, and that gives us a total of 27 cubic inches. So the total area times distance is 54.5. And we now want to divide that by the total area of the entire shape, which is 23 inches squared. And what we find is that the centroid of the T shape is at 2.37 inches above the reference axis. So that is, in a way, kind of a surprising result, right? The area of this flange has actually pulled the centroid from, if we were looking at this symmetrically, from 4 inches down almost 1.75 inches, right? And what that means is that this web now has a lot more leverage over the centroid than it would have on its own. Right? We have moved the neutral axis, and therefore we have given this thing a fair amount of leverage that it didn't have before. The neutral axis, again, is where we have zero stress. So if we go back and think about it, the centroid here is actually, a T-shape is actually not such a great beam shape in this case, because we have a huge amount of cross-sectional area that's right around the centroid. This is why when we're designing beams, we typically do an I-beam. So we put another flange on top. We pull the centroid back into the symmetrical middle of the beam, get it away from where we have a lot of cross-sectional area, way of making the beam more efficient. If you look at steel construction, you can see this principle at work. Whenever we have penetrations that we need to put through a web for mechanical reasons or otherwise, our engineer is going to be fine with that if they're in the web, and they're going to be happier if those penetrations are closer to the center of the beam. So here you can see this is a set of steel beams that's got a lot of penetrations in it, a lot of ductwork going through those beams, and the engineer is fine with it because the web is not the part that's doing the work in bending. It's the flanges, and so long as those penetrations are close to the center of the web, it's not really affecting the strength of the beam. It's affecting the strength of the beam in shear, of course, but in bending, those penetrations aren't hindering it very much. It's mostly the flanges that are doing the actual work. Now, because the stress distribution is a straight line, when we pull the centroid down one way or push it up another, as in here where we have two unequal flanges, we change the stress distribution. And in this case, for example, we're making this flange work much, much harder because we've pulled the centroid down much, much further, right? You can see that the stress in this top flange is much higher than it would be in a symmetrically loaded beam. The stress in this flange down here, much, much lower. This is an argument usually for symmetrical distribution if the material is equally strong in tension and compression. An example of where this isn't the case is those cast iron beams that we looked at briefly in British mill construction. Here in a mill that Fairbairn did in 1834, you can see the cross-section of the beam is asymmetrical. And we might look at this and think, well, maybe Fairbairn didn't know that the stress was going to be asymmetrical and that this top part was going to be so much more stressed than the bottom flange. Well, in fact, Fairbairn knew exactly what he was doing, because these beams were in cast iron. And cast iron is about 6 times as strong in compression as it is in tension. Today we design with steel that is equally strong in compression and tension, so it makes sense to have flanges that are exactly the same size in cross-section. In Fairbairn's day, working with cast iron instead of steel, you can see that he knows to make the compressive flange about 1/6 as large as the tension flange. And that's perfectly appropriate for cast iron. That's exactly right. That's pulling the stress diagram to make sure that both of these flanges are working at their peak capacity given the stress that they're under. Today, working in steel, we're looking for more symmetrical sections. Okay, here's where things start to get fun. If we know where the neutral axis is, we now want to know not just how much area we have in the beam or how deep the beam is, but we want some idea of a kind of hybrid figure. We want to know where that area is located. We want to know how much moment arm or how much resisting moment the area of that beam can actually build up. So the moment of inertia is a measure of basically on average how far the area in a cross-section is from the neutral axis or from the centroid. In general, not quite perfect, a higher moment of inertia means a more effective resistance to bending, because it means that we have more area, but also that that area has a higher moment arm, right? A larger moment arm that allows it to twist back, right? To resist the external moment that we're putting onto a shape. We find the moment of inertia by summing up the shape's area. and that area is distance from the neutral axis. In other words, the strength that each little fiber is capable of building up times its moment arm within the shape. And whenever we're summing up infinite numbers of infinitely small things, we end up doing a little bit of calculus. And I'll sort of skip through that just to say that the math of it looks like this, that the moment of inertia for a shape equals all of the little moments of inertia, so the moment of inertia for each little bit, plus its area times its distance from the neutral axis squared. In a separate kind of bonus episode, we'll go through a little bit how we come up with this and why it works. For the moment, if you don't want to get into the math, you can just take my word for it. We'll get there. We have pretty well-defined formulas for moment of inertia. So for a rectangle, it's the base times the depth cubed over 12. We get this again from calculus, doing an infinite number of infinite sums. And we have kind of related but varying formulas for the shapes that we might come across otherwise. So triangles, depending on whether we're taking moment of inertia about the tip, the centroid, or the base. And moment of inertia for a circle, interestingly enough, pi shows up. And you can see that the depth counts for much more than anything else. There's one base times depth that gives us the area. There's a depth squared that comes from the calculus that gives us the kind of area times distance from the neutral axis. What you really need to know is that flat shapes have low moments of inertia and deep shapes have tall ones. So this is math that jibes with our intuition about what a strong beam shape is. If we run and do the math just on simple rectangles, a 1x4, here's the formula for moment of inertia for a rectangle. The base in this case is 4 inches, depth is 1. And you can see that if we run that for a flat shape, we get 4 times 1 over 12, or 1/3 of an inch to the 4th. Exotic units there, but don't worry, we'll get to something a little simpler in a minute. If we flip that around, right, all we're really doing is changing which is the base, which is the depth. Take the same shape, if we make the depth 4 inches and the base 1 inch, then you can see that we're benefiting from 4 cubed instead of 1 cubed, and we end up with I being 5.33 inches to the 4th, give or take about 15 times as strong in bending as a flat shape. If we take our little T shape and run through the summing up the moments of inertia, we found our centroid before. Here is a lot of complicated math that tells you basically that the moment of inertia of this rectangle and the moment of inertia of this rectangle, when we put them together, notice that each one individually has 10, 13 inches to the 4th. When we put them together, the distance that each one gains around its centroid, that extra depth, gives us a moment of inertia of 86.5 inches to the 4th. So we might think that we would, sort of roughly double the moment of inertia, or double the area, a little bit more than double the area by combining these. And in fact, while we might double the area, we're getting something like 6 or 7 times the strength in bending by increasing the depth and the moment arm of all of those little areas put together. Just like the examples I showed earlier, we can take the same amount of area and we can manipulate sections to gain an incredible amount of bending strength. So each one of these shapes is 100 square inches of steel, but the moments of inertia, effectiveness in bending, again range from about 208 inches cubed for the round bar. Notice that most of its area, cross-sectional area, is concentrated right around the centroid. If we go up, if we make that into a 28-inch deep Ibeam, we have a moment of inertia of 13,000. So about 500 times the section, or the moment of inertia of a round bar. And here you can see by increasing the depth, we have a moment of inertia of 75,000 inches to the 4th. So this means that this is 75,000 times almost 5 times as effective a beam as a round bar. And this explains why when we're dealing with steel construction especially, you see I-beams everywhere, because those flanges and the depth are exponentially more effective at carrying a bending load. Who else is interested in moments of inertia? Professional bowlers. Why? Because a bowling ball for professionals is hollowed out and has most of its weight concentrated around the exterior of the ball. It makes it harder to get rolling, but if you've got strong wrists, once it gets rolling, it makes it much, much harder to stop. One of the reasons that the figure is called moments of inertia. Structural engineers are interested in putting the cross-sectional area of a beam as far from the neutral axis as they can. And you can think of what those flanges do, right? The resisting moment that they impart to the beam as analogous to the inertia of a professional bowling ball, one that's not only heavy, but that has most of its weight on the exterior. Therefore, hard to get rolling, but also very hard to stop. Okay, finally, section modulus. This is the figure that we actually use when we're calculating beams. The moment of inertia is measured in inches to the fourth, and if you think about it, what we're really interested in is inches cubed. We're interested in the area, square inches, times that area's moment arm around the neutral axis, one more factor of inches. So because the calculus is important to getting to moment of inertia, we end up with this extra measure of length. And in the section modulus, we actually take out one factor of length to get to something that's pure area times moment arm. Just like moment of inertia, the higher the section modulus, the more effective the beam. Since depth is already part of the area, we take out this factor of depth. And the way we do that is we find the distance from the centroid of the shape to the farthest edge of the shape, what engineers will call the furthest extreme fiber. We'll call that C. And section modulus is just very simply a shape's moment of inertia divided by C. If we or our engineers or fabricators are calculating the section modulus from a bunch of built-up shapes, we have to do that using moment of inertia and then come back and divide this out using C. The good news is that for most common steel shapes and timber shapes, we can simply look up section modulus and shortcut all of the math that it takes to get us to moment of inertia. So here, to find the section modulus of our T shape, we take the moment of inertia that we found earlier, 86.5 inches to the fourth. We look at the centroid and we try to figure out where the farthest fiber is. In this case, it's going to be the top of the web. Bottom of the flange is just 2.37. Top of the web is going to be 5 plus this remainder here. And you can see that what we end up with is a C of 5.63 inches. And if we divide moment of inertia by that, we get a section modulus of 15.36 inches cubed. And that kind of jives, right? That tells us more or less not just how much area we have, but where that area is in relation to the centroid. A measure of how much resistance and where that resistance is, how much resisting moment it offers us around the neutral axis. Okay, like I said, for simple shapes, we can just look this up too. So you can see that section modulus of a rectangle, we're taking out one factor of depth, or 1/2 depth. So we end up with BD squared over 6 from BD cubed over 12. And here are the section modulus figures for our other two common shapes. Now, the section modulus is useful because we can go through and we can figure out the relationship between moment and stress and distance from the neutral axis to the extreme fiber. This is a lot of thought experiment here. I will go through this in a little bonus video. It will not be on any exams or problem sets. I think this is a particularly beautiful piece of math. And the good news is that after we go through all of this, what we end up with is that the total moment that a beam is able to resist is very simply equal to its allowable stress in tension and compression times the section modulus of its shape. So for all of this complexity, for all of thinking about moment of inertia and infinitely small fibers and stress triangles, we end up with one of the most simple possible equations to figure out one of the most important jobs in structural engineering. Namely, how much moment can a beam carry? Well, the moment allowable is equal to the allowable stress in tension and or compression times the cross section of that beam's section modulus. If we are designing in a material where we know the allowable stress, if we have a section where we can either look up or easily calculate the section modulus, we can do a simple calculation, just multiply those two together, and that will tell us how much bending moment the beam can carry. We've already gone back and we've looked at how to figure out the maximum moment in a beam. We do a shear moment diagram. So we now have all of the tools to be able to calculate a beam and bending, a problem that should be super difficult. Galileo didn't know how to do it. Leonardo didn't know how to do it. We have this very, very simple calculation that we can do that allows us to, once we know the moment that we're subjecting a beam to, once we know something about the material, once we know something about the geometry, we can put them together very, very quickly. This also, I hope, explains why when we're dealing in bending, we see shapes like this all the time. The W shape or the I-beam is basically the mathematics of cross-sectional shapes, the mathematics of deriving section modulus in steel or in concrete or in whatever other material you're doing this in. You will almost always find that beams want to have flanges, usually symmetrically placed, and a relatively thin web, so that most of that beam's cross-section is pushed out to the very, very edges where it's doing the most work. Note too that we'll often find webs with penetrations in them, usually for mechanical systems, and that is another benefit of the W shape, that the web is basically lazy material. It's working in shear, and as we'll see, it's working not only in vertical shear, but also in horizontal shear, keeping the flanges together. But those stresses are typically much less than bending stresses, and they're much less than the tension and compression that those flanges are going to experience. The other good news is that we not only know a lot about steel as a material, but the steel industry has made sure that it produces standard structural shapes where the section modulus is both reliable and widely published. And so going back even to the early 20th century, we find tables like this, where for a given steel shape, and we'll talk about what these numbers mean in the next lecture, we have not only the moment of inertia, we also have the section modulus. And this column right here is what we'll use to actually select beams once we know the maximum moment that we're applying to them. So just for some comparisons, we'll come back to this when we talk about columns too, because this figure down here measures column effectiveness more than beam effectiveness. But here's what we're looking at for this week. Section modulus, and here again taking areas that are pretty much exactly the same, 24.5 inches. Looking what happens when we go from a rectangular section, already a fairly strong beam, 55, 56 inches cubed. When we turn that into an I-beam, we see the section modulus more than double, right? Same amount of area, same depth, just being clever about where we put the material. If we flip that around and do a flat beam, exactly the same bit of steel, we find that we're only about 10% of the strength in bending. This explains right here why flat beams are worse than deep beams. And if we do an I-beam section there, we're gaining a little bit because the flanges are tall, so we're getting back some depth. But notice that the section modulus is still much less than if we do an I-beam in the correct orientation. Okay, in the next little bit, we will look at how we use these three factors, maximum moment, allowable stress, and section modulus, to actually get in and design and select beams. We'll look both at how we do that for simple loading, and then we'll look at the very important step of thinking about the beam's self-weight and the discussion that we'll very often get into with engineers between whether we want a beam that is much, much deeper, often what the engineers want, and lighter, or much, much shallower and heavier.